the location of a line under a mobile robot by me, Kirk. And I have to give a shout out to two people, only one of which is on here. Ben Axelrod really helped me hammer this out over at Chick-fil-A, and also Jay. We were brainstorming together. He came up with a vector way of doing this that basically did the same thing, but this way is actually a little simpler, and we use Jay to beat our ideas against it. Oh, that's sad. That doesn't really show up well. But anyway, that's a gratuitous photograph of the bottom of a robot. And you can see the little sensors across here barely. And we can turn off the lights for 23 seconds, and people can see.
I promise to stay awake. Okay.
Yeah, but I don't promise to stay awake. So anyway, there it is. Okay, moving on. So first I want to talk about prior art. What else is out there? I mean, there's lots of ways that you can determine where a line is. If anybody is not familiar with the sandwich robot, highly recommend you go to robotroom.com. And Dave Brown has some awesome stuff. He has got a couple books out. In one of these books, he details the sandwich robot. Just two sensors. What we call bang-bang control. Only one wheel at a time is running. So if the line is on this side, you turn that way. If the line's on this side, you turn that way, and it just works its way down the. It's just got an analog comparator that looks at the thresholds of the two sensors and determines the action with a couple transistors. It's insanely simple. So, a way to do two sensors. Three sensors. Parallax.com has a really good example of this three things. It's 5 case statements. If the sensor 1 is active, turn left. And 1 and 2, turn left a little. Sensor 2, go straight. 2 and 3, turn right a little. Sensor 3, turn right. Sensor 1 and 2, or 1 and 3, that should say 1 and 3. Yes. Change that. Panic. You have no idea what to do in sensor 1 and 3. So anyway, this is not very simple. I mean, there's a lot going on here. It is not very easily scalable. If you try to do this and add, 7, 8 sensors, you're going to have a lot of bizarre code. It's not proportional. It doesn't handle exceptions, except for this exception is not an exception, but oh well. And does not handle variable contrast. You're looking for a threshold and you're saying there's a line or there's not a line. And it's not my favorite method.
Really?
Another one that you guys need to look at, and you can easily memorize this web address.
There's a web address there? If you can see it.
Yeah. No, you can't. It's on the Seattle Robotics Club website. You have to dig for this robot, but it's a very, very cool robot called the Desktop Line Follower. You might be able to Google Desktop Line Follower. It just has two little coin cells on it, some really small sensors, a surface mount Mega 8. It's a great little robot, and a very nice article about it. How he does this is he picks 2 adjacent sensors that have the highest value and does a linear interpolation between those values. So advantages are it is proportional, so you can do PID loops, and he's got some great videos on what a PID loop can do for you. It does handle variable contrast because you're just looking for the highest 2 numbers of a continuous range. Not too easily scalable because since you're having to select between the highest, you have to do some thinking about how you're going to do that. Not horrible, but it is scalable, just not super easily. It doesn't handle exceptions like what happens whenever you have a split line or a maze intersection or something like that. Question I thought might come up: what do I do with proportional line information? Since there's so many examples out there of either bang-bang controls or discrete controls, it's like, well, what do I do with proportional line information? Cool thing about this is I can steer proportionally. If I'm 3% off the center of the line, I can steer 3%. If I'm 80% off the line, I can panic. You know, you might want to reverse a wheel in an extreme situation. You can perhaps add a PID loop. This is stolen from the Seattle Robotics website, you know, showing, hey, you know, this right wheel, you know, if the steering command, if the line is over here, you can slow down this wheel that much. And so that's some of the advantages of proportional line information. Okay, so now that's the history and prior art. And the bragging slide. It's simple. It's scalable to any number of sensors, 2 to whatever. It's adaptable to other sensing environments, whether it's obstacle detection, opponent detection, stuff like that. And of course, you get proportional output for smooth control. How does it work? Imagine that each sensor has a spot on a seesaw, and each number that the sensor gives out is a brick. And so this guy in the overalls is an Arduino, and he is stacking bricks on the seesaw. He has intuitively chosen this spot as the approximate balance point, just because he knew that when he put that fourth brick on there, that's about where it's going to land. And that would be where the line is. You just shift that fulcrum back and forth, and there you have it. That's most of the presentation. So how do you do this mathematically? By the way, this is where we're going to start getting questions. Anybody has a question, feel free to jump in and ask, because it's not necessarily in everybody's intuition how this actually works. So we're going to pick an arbitrary pivot point.
Are you posting these someplace?
No, this is secret. Only to be within this room. Yeah.
You have to show up to the semi-regularly scheduled annual.
The fourth semi, almost approximately annual. Yeah. Now I did actually tune this presentation up from last year, so it makes a little bit of sense without a live presenter. So hopefully you guys can be the judge of that. So I'm going to pick an arbitrary point for the pivot point, left side, random. I'm going to put bricks at the sensor position. So sensor 0 gets placed at 0 position, sensor 10 gets placed at 10 position, and so on out. The number of bricks is equal to the sensor value. I'm going to take the mass of every brick, multiply it in the units of bricks, and multiply that by the distance from the pivot point. That's my torque. Divide that torque by the mass, and there's my line. Okay, so let's, here's a sensor. Where's this line? Anybody? In the middle. Okay, let's look at the math. Oh, how about this? 15, 18, 180, 180, 12, 18. Mass is 423. The torque, 10,000 and some. Centroid's at 25. No surprise. Where's the line here?
By 50.
Right of the center.
Little right of center. 50?
28.
Excuse me, you're excused. Yeah, 27, very close. Jebediah doing a little math in his head there, and he missed the rounding.
Floating point error.
Yeah.
Yeah, we'll actually get into that in a minute. Yeah, I mean, is this intuitive now? Oh, 15. Wow. You guys are getting close, though.
You're
Okay.
veering, Dale.
Yeah, all right. Line here is way left. It's kind of time to panic, right? Here's a little interesting bit of information. Centroid's at 9, but the line is probably at 2, right?
I use 1 for that value, just so it's not always 0. Like when I do this, that's the big difference between what I took from you is I make that 0 into a 1.
Then this would have to be 11.
No. Just because I don't want all that stuff being 0 all the time, so I like to keep that in my
Was 0 a bad thing?
After you've finished all the
I would
math,
rather
add
a
1 to it, in case you divide by it.
You never divide by the answer.
Or if you multiply.
And
Multiply by 2. You get 0 out.
anyway, let's just stick with this being 0 for now. This is a question that last year had all sorts of issues and questions, and I do want to keep that dialogue open because there's some interesting thoughts on that. Okay, let's look at another one. Where's the line here? We have no idea where the line is, right? It's not under the robot. How do we know that? Just intuitively.
Because of the mass.
Because all these sensor values are
Well,
really low.
Yeah, there's the mass.
But then how do we know this mathematically?
yeah, if your
Because
mass
of the math.
is-
Thank
yeah.
you, Jeff. And yeah, so we set a threshold. Hey, the mass is below some number.
50.
Well, mass is 89 now.
Yeah, all right.
So we have to, you know, we can go.
100.
Yeah. All right. Where's our line here? Out there. Interesting about this, and we'll get into this in a moment. Our centroid is at 32, way over here. Clearly the line's a little over here. One question is, do I care that my answer is slightly off? You have to kind of ask yourself that question. The answer very well may be, no, I don't care, because I know that the line is somewhere over on this side, 25 being the middle. Line's over here, steer that way, life is good. I can tune my gains to work, and but there's ways we can enhance these answers a little bit. But the neat thing about this system is, handles very low contrast without doing anything, really. High contrast, low contrast, whatever, you don't have to be thresholding your sensors or calibrating or anything like that. It figures it out. Where's our line here? Or what's our situation? Maybe not.
Like
No.
T or something.
Probably.
Yeah, a really wide line.
A very wide line. That's a great possibility.
Or a right-hand
Or a
turn.
cross.
Pardon?
An intersection.
It could be an intersection, like a T intersection in a maze. So another neat thing about this system, though, is it handles wide lines. If you're picking, between the two highest sensors and you hit a line that is 6 sensors wide, you're really subject to noise. You don't know what you're getting. This, it's like, hey, Centroid's about here, 34. Turn that way. If you're doing maze, you probably want to be taking this, number 50 sensor and number 0 sensor out of the calculation and using that as simply your intersection detect. But how to do it. All right, so channel 1, we're going to have 6 analog channels in this scenario. I'm going to loop through all the channels. I'm going to assign a variable sensor value to whatever that analog read is. We'll talk about this divide by 32 in a minute.
Mentioned you're getting 5.
Pardon?
The way you set your loop up, you're only getting 5.
That's all he has.
Oh, well, okay. You can fix that before it gets posted
Just
for me.
saying.
Yeah. Is anyone taking notes on all my errors? That's 2 so far.
Yeah, just 2, you're good.
Okay, good. Thank you. So, yeah, let me kick the screen here and make it really good for the video. If anyone's not familiar with this little C shorthand, plus equals is the same as mass equals mass plus sensor value. So we just, for each sensor, except the 6th one, we're totaling these guys up, or except the 0th one, right? And the torque, sensor value times the channel. And at some point or another, I need to multiply this by 10. And we'll talk about that in a moment. Come on. All right. So there's only 2 integer variables here, not counting the answer. So you can do this on any small micro controller, at least that takes in analog. But the frowny face one is it does not account for background variations. So You have that low contrast issue. We're not really accounting for that very well. And these factors, the reason for the divide by 32 is, do I really need 512 levels of gray to determine where a line is? No. Divide by something, 32, 64, whatever, and I can just reduce the amount of data I have to process. I like to multiply by 10 here because I don't want to do floating point math. So just, instead of the line being at 2.5, I'm saying the line's at 25, and I don't have to do any floating point or fractional math.
So explain the 32 a little bit more. If it's within the size of the integer, why does it matter?
Well, let's just suppose that
A to D is a 11 or is a 10-bit.
well, let's just say I've got an 8-bit A to D, so it could be 0 to 255, right? Then I'm going to multiply that by, I'm going to add those all up. Let's suppose we have that situation where we hit the maze intersection. We have lots of high values, and then I'm multiplying that to get the torque by 10, 20, 30, 50, and then this number would wind up overflowing.
All right, you're already in trouble with an 8-bit microprocessor.
Well, yeah, these have to be 16-bit values, for sure.
The issue with the 30 divided by 32 is if you've got a 0 to 256 or 255 range, low value, like say 20 divided by 32, you got 0.
Yeah, you're right. I do this differently now, actually, in my robot, now that you mention it.
So,
Oh, you're setting us up so that you're better than
No, I don't know what I do. I don't remember. I think I divide at the end.
yeah, divide it.
I think, yeah, that's what I do.
Just use an ARM, you got 32-bit ends.
So, okay, so this divide by 32 should be down here, below, at the end of the 4. Okay, that's 3. And then this multiplied by 10 should be somewhere else too, so probably.
Question about your pivot point. So I see torque plus equals sensor value times channel.
Yes.
How would that be altered if you moved your
You would just make the math way more complicated.
Oh, okay.
No, that's a great question because you can arbitrarily pick the pivot point. But what you would have to do is, let's just suppose my markers are over here. That is a great question because this was brought up by somebody that puts their pivot point at 1 instead of 0. So let's do 4 for sake of simplicity. So here's sensor 0, sensor 10, sensor 20, sensor 30. And if I pick my pivot point at, let's say, here, then I stack up bricks here. And that's our background noise, and then we're going to put another brick here. So if I put my pivot, my green pivot, at 0, so my green math is going to be, the mass is going to be the same, right? 5, always. But my torque, about the green pivot, is going to equal 1 times 0, 2 times 10, 1 times 20, and 1 times 30. So I can just loop right through that, right? Well, this way, when I do the orange one, the torque is going to be 1 times 0 minus 30, 2 times 10 minus 30, etc. Or, of course, I could simply just renumber my sensors. So it is truly arbitrary whether you pick the left or the right. It's just nice to have your your pivot point sensor 0 because it just makes the math easy. Now, the next question would be, well, what if I put the pivot in the middle, and then you've got positives and negatives, and you have to deal with signed integers. And I just chose to make it simple and deal with unsigned, non-fractional numbers. But
How many bricks you got on 0 multiplied by 0 is still 0.
right,
You don't have to do that calculation.
So maybe that's why you started at channel 1 instead of 6.
that must be it. Yeah, that must be it. Because it certainly wasn't that I forgot.
It doesn't work. Let me try sticking pins in it. Oh, when I change this from 0 to 1, it works.
Yeah, you could have just started at 10, it doesn't matter. Go 10, 23.
Well, I still have to add the mass up, though.
Sure,
Yes,
absolutely.
that you do.
Yeah.
It all normalizes out at the end.
So, yes, I could save a multiply cycle, which, we all know how precious those are.
Well, if you're using a pick
Yeah. Okay,
or a stamp,
advanced implementation. Let's do this a little bit better. Let's read all the channels, put all the results in an array. We're going to find that minimum reading and call that our background noise level. Subtract that from all of the readings and then redo the calculation. So we get better noise rejection. It's still easy to process. It's no big deal. It becomes perhaps an issue if you're having, integrating 1,000 sensors. You have to have a 1,000 item array. But, uses a little more memory. Not a big deal.
uses a more memory.
Yeah, you have to correct the bottom line on that last one.
What's it say?
Uses a more memory.
Oh, perfect.
The other backwards.
The other backwards. This backwards? Oh,
Keep
awesome.
going. What are you doing?
We're making a mess here.
Other previous. There you go.
Oh, uses a more memory. Well, this was actually the Chinese translation.
I was thinking more was manufactured.
This was the English translation of the Chinese translation?
Yeah, something like that.
Of the English original?
To the
All right.
English.
Back.
Or was it the Chinese original?
So here's our old calculation of 32, slightly out of focus.
Welcome to the real world.
Yeah, okay. And so we have our sensor numbers, our readings, our adjusted readings, where we're subtracting 9, and our adjusted torque. And we see, hey, we get 36 instead of 32. So we're closer to true line position, and not as influenced by some of this other stuff. I don't do this, Dale does. It's kind of depends on what you're doing. I would say if you're doing obstacle detection, you definitely want to do this because you want to be able to detect something really far away. Whereas, for a line, we know it's not very far away.
There's such a big swing on a line when you're over it or not.
Right.
I mean, you don't
Whereas
really need
obstacle
to.
detection, you might have something like this very readily if you're doing obstacle detection. So this kind of advanced implementation is very important.
Doesn't that just fundamentally deal with the delta data, and therefore your error is less?
Yeah, I mean, you're getting, exactly, because I'm subtracting out this number, so basically I'm just drawing a line across the middle and recalculating above that line, throwing away the bottom bricks. Just some AVR specific notes for anybody that uses it. AVR's got an adjustable clock on the ADAC. You can slow it down if you need real accuracy, but we're doing lines, who cares? And there's a bit you can set to get 8-bit results instead of 10-bit results. Just save a little bit of math, and nobody cares about the last item. Sensors. My favorite sensor, the QRB 1114. It's got awesome visible light rejection because it's got an infrared daylight rejecting filter. It's got a long focus distance, good ground clearance, 1/8 of an inch ground clearance, easy. Fairchild decided that because it was my favorite, they would punish me. It is discontinued.
That was mean.
Yeah. There is the QRD, Quebec Romeo Delta 1114. Kind of similar. This also has a daylight. Yes.
I was going to tell you, Optronics had that basic case as well.
Really? I
with
couldn't
the
find
IR
it.
filter. It's a pretty much a standard.
Is it still out there?
I can't tell you, I've been bought them about 5 years.
Yeah.
But
Well, it's
But
about,
that-
that's
that
about
full-
when, it's
that
about when I
case
bought
si-
my others.
that case size you had there, though, it is standard. I've got
Yeah.
a few.
Yeah, Lynx Motion had one about 5 or 6 years ago, the same
Yeah, I know,
case.
it's the same one, and
Oh,
it's
is it?
discontinued also.
Okay.
So, I've looked around, I'm not saying they're not out there, the,
If you
But-
found one in the last year, let us know.
right, that's the issue.
I'm not gonna put my-
This is unfocused. Gives a fair ground clearance of a 16th, and I'll give a little bit of a caveat there, if I can find an eraser. That sensor, if you look at the data sheet curves, its sensitivity is something like this with distance. And that distance is somewhere around 0.03 inches. And here is somewhere around 0.05, something like that. So that's where your peak sensitivity of these sensors is. But the caveat is, do I really need to operate at peak sensitivity? Because I'm saying, hey, you got a 1/16 of an inch of ground clearance, and that's true if you strictly follow the data sheet. But I think Don has done this with a similar sensor, where he's running it way out here,
Yeah, that's what I'm doing.
and it's not as sensitive, but you're still getting good swings, you're still getting good data.
As long as all your sensors are at the same level, they should have the same sensitivity.
I want to bring up a point, this juncture about those sensors. Their sensitivity, absolute sensitivity varies from part to part.
Right.
They're not all exactly the same. It's a considerable amount, maybe up to, I don't know, 50% or something.
5.0?
I mean,
Wow.
I've seen some that are way out, but most of them are like within 10%.
Right.
And anyway, in order to get good histogram results, all the sensors need to be pretty much matched. And you can match those by changing the load resistor on, so that all of them have about the same gain, so to speak, by just changing the load resistor on the photodiode, phototransistor point.
So you're saying you could put trim pots there or
Yes.
something?
In fact, I've got one of those 16-pin headers that plugs into an IC socket with 8 resistors that I select each individual resistor to match them.
So this resistor you're changing
Yes.
to tune. I guess that's the other advantage to the obsolete part that you can't get anymore is they were all consistent. At least the 6 that I've got, but I got lucky.
Well, I don't know, if you measure, you know.
Yeah, I mean, I can check the readings as I shift across the line, and they vary by a couple of points out of 512.
Oh, really?
I have a data sheet. I'll try and find the link that I got. I think it's Philips Semiconductor. They have comparison of all the different technologies of infrared sensing for close.
Yeah.
The
So we're looking
benefits.
for far away. And I wonder
Oh,
also
for
if it's
that line,
part of
okay.
the fact that
It may very
you're
well
you're
be
in
that
you're in
it's-
this section of the curve
Yes.
here.
Yes.
And since they're an unfocused device, if, the manufacturing variation of that, where that beam is aimed, you could be shifting way up in here, and I'm curious, I don't know, but if you were in closer to the peak sensitivity, if that would be less.
Well, if you're right at the peak, it might be less. You see that steep curve you've got coming down right there?
If I'm here,
That right there would be the worst case.
right,
Was that a log scale? Even worse then.
I don't remember. I don't know. Somebody can quickly look up the QRD
The one-
1114 data sheet for us, and we can find out.
Well, going along with what Dale says, there's two things to consider when you're doing this, if you're trying to handle it in the programming. One, you've got, like Dale says, gain to deal with, gain differences, but you also have offset differences. And this does compensate to some degree the zero offset of the same light sensitivity. So you've got a change of gain, but you also have a change of level, start biasing.
And it would be easy enough to do, measure a light spot and a gray spot and kind of figure that out and determine where your slopes are.
Yeah.
So it's certainly worth what Dale is saying. is, you know,
But
tune
you
it up,
can't-
check it out. I mean, what I did is I built my robot. I didn't allow, well, actually I did allow for compensating with resistors in little headers. But I shifted the robot back and forth across the line and watched all the sensor readings, and they were close enough for me. And if I were doing obstacle detection, you probably want to be more fussy about tuning out to get those even. More thoughts? Cool. And another gratuitous robot photo. And questions? That's it.
Can you go back to the C code?
Absolutely. You mean that where we found the error?
Which one?
All right. Yeah, let's see which slide that was.
6,
Slide 6?
maybe.
All right.
That neighborhood.
There it is.
I didn't bring my notebook.
Okay.
You use notebooks still? You still use notebooks? Point your camera at the projector.
Oh, another thing, your motor
John, your
picture,
motor
when you're scaling down your motors,
Yes.
that goes up to a point. What I'm doing is it's a plateau at the top, because since it is a speed competition, just you get a little bit off the line, you don't want to start slowing down, so you have a dead band.
Oh, okay. Yeah,
If it's on the first, like,
that was way back here.
yeah, somewhere between, say, 25 and 35. So on your scale,
So
if you're
what-
between 25 and 35, you're still going full speed on both motors, because you're not off enough to care about compensating yet. Otherwise, you might not be able to see it, but your motors are actually compensating at every moment unless you're dead on 25.
So you just
So-
got a big flat spot.
Yeah,
So
so it's
you're
good to
saying
have a
it's a dead
good,
zone.
yeah, a dead band at the top. I have, I think, 3 zones. Whether if it's on, because I have 8 sensors, if it's just on 4, 4 and 5, or just 5, which gives me between a value of 30 to 45 is my Centroid dead band. If it's above there, then I start dealing with the motors. I think that gives you more speed overall. You might get a second or 2 out of the whole thing, but still something.
I'd love to see a side-by-side comparison of that. That would be. So this is what you're doing.
I'll make a whole nother robot, exact same specs, and run them together.
You just changed the code.
You know?
I think you want to make it totally linear and have no dead bands, because if you get it tuned right, once it gets dead center, it's going to go full speed straight down that line. Any slight variations to make slight tweaks to the tune. If you put a big dead band in there, it's going to start bang bang, and there's you're going to waste a lot of energy.
That's what I was thinking. When you're in that dead band, you're not noticing any variation until you're
way off.
or perhaps noticeably off.
Right.
I agree partially with that too.
Yeah. I mean, but I don't know. I can't answer that because my robot's slow. I mean, this was all developed and, had a winning robot, and since I presented this, everybody is using this and has totally eclipsed my speed. So,
That's not the problem.
Just add bigger
You got slow
wheels.
motors.
well, yeah.
Just add bigger wheels.
Right.
Who
More
cares? Who
sensors.
cares about torque?
But also I'm running 24-volt motors at 9 volts, so that might have.
Oh. No, you're supposed to run 9-volt motors at 24 volts.
Oh, okay. Damn it. But I actually do something a little different, and that is, okay, instead of dead band, we'll just get rid of this. I'll only do one side. My speed does this, and I reverse a motor when I get way off. So that in advanced line follower, there's some very sharp turns. And instead of just trying to, depend on swinging around and hopefully finding that line again. You know, just pivot now and stay on the
So
line.
you're reversing, because I reverse when I've lost the line completely, but then I'll spin in place. But when you're at the very edge of your sensor array,
Yeah, it's some threshold, I don't remember, you know, let's say 35, you know, steering command, I go into panic pivot mode. And, you know, same thing over here.
That's pretty much what I've done. Once, when the 90-degree turn, it's a special case
Right.
where it sees which side it had before it lost the line.
Yeah, then you've
And
passed that line.
You passed it, so you do a pivot and say reapply.
Right. So that's the other thing that I do is if I've lost the line, you know, if my mass is below a threshold, then I do whatever I saw last. What was the last thing I did, and do that. And if I just, you know, see that line way over there, then I'm gonna pivot and find it again. So at some point or another, you know, somebody is gonna experiment maybe with parabolic and logarithmic and all these things. But at least in the slow speeds that I'm running, a simple PID loop that, you know, locks it in pretty tightly, and mostly I add a little bit of, probably a little more derivative factor to kind of reduces the zigzag hunting. We could talk about PID loops in some other presentation. Yeah.
Fun.
Yeah, it's fun.